We have our first speaker already prepared here. Ellis will tell us more about a paper on Apple's Find My network.
Hello, everyone. My name is Ellis Fenske. I'm presenting joint work with Travis and Eric at the U.S. Naval Academy and Airbus on Apple's Find My network and some flaws that we found in it and a solution to try to fix them. So let's get started. First, I want to introduce the notion of crowdsourced location tracking, which is a phrase that's come into use in literature to describe these sorts of technologies. Sort of the ones that you can see pictured here. There's probably a lot of these devices in the room, definitely at the conference, AirTags and other such devices. So let's talk a little bit about how they were introduced and how they work. Apple introduced these AirTags, which are at the top right, in 2021 as part of their Find My network. Other Apple devices participate in it as well, but AirTags are probably the most well-known element that participates in this network. And other companies have quickly followed suit, providing similar devices that are following basically the same principles and trying to achieve the same goals in the same form factor. And so these devices all use Bluetooth Low Energy advertisements, which are small little beacons, and they don't take a lot of power, and so they are suitable for a small form factor, small battery, cheap device that you can attach to anything like your keys or a bag, and then the device will just emit these small little signals. They don't take much power. And thus, the battery on these devices can be really long, like a year or 2 years. And so you can buy an AirTag for $30, and it'll emit these signals for 2 years without changing the battery. And then the idea is that these devices are so cheap and small that they don't actually have GPS or Wi-Fi radios in them, so they don't know their own location. Instead, what they do is they send out little advertisements, and nearby iOS devices or participating devices for the other services will record the beacons and use them to report their own location. So you have an AirTag, and it cruises around the world. It sends out beacons, and then you get the location of the closest iPhone to the AirTag if you want to try to track it. So they're designed in order to help you sort of find your items, your devices. So let's talk a little bit about the details of how this works. Part of our contribution was to introduce a formal model for these crowdsourced location tracking services, sort of talk about how they work in general. But also we looked a lot at Apple's implementation and tried to make some modifications to make it better. So I'll talk both about the formal model and also about the implementation details for Apple. Those will be in blue. So there are 4 parties in the protocol. First, there's the tracking device, and then there's a bystander device, which is any device. All Apple devices are by default enabled in this network. And then there's an owning device, which I've sort of displayed it as a computer, but it can be an iPhone as well. And finally, there's the server, which in our example is Apple. And so the first thing that happens is you buy an AirTag, and you pair the AirTag to your account. And so what happens is there's some protocol that occurs potentially between the AirTag or the owner and the server. And so what happens is some secret material is distributed to the server and the owner. And in Apple's implementation, what happens is the secret material gives nothing to the server, so the server doesn't have anything. But the owner gets some key material, a master beacon key, which will be used to produce the advertisements later. And crucially, the owner can give some or all of the secret material to the AirTag, which it will then use to broadcast the beacons. And then when the AirTag wants to broadcast a beacon, it will look at the time, the current time. And in our talk today, the time will always be based on a day. It's not any more granular than that. These keys change daily. All of the epochs are 1 day. And it will broadcast a beacon however it's designed. In the particular Apple implementation, it will apply KDF to the master beacon key and the current time. That will produce a key pair, and it will broadcast the public key. So all it's doing is it's broadcasting a new public key every day in these beacons. And this is actually the exact packet diagram for the beacon format. And I don't want to go over too many of the details of the format. You can look in the paper. But what I do want to emphasize is the fact that the key, which is a P224 elliptic curve public key, will not fit in the payload for a BLE advertisement. And so what they've done is they've taken some of the key bytes and put them in the MAC address, which typically is random, but here actually contains key material. So the point here is that these payloads, these beacons, are jam-packed with key material, and there's no room for anything else, which will become important for our talk later. Then, when the bystander wants to generate a report because they've seen a beacon for a nearby AirTag, what they do is they take the beacon and they pull the public key out of it. and then they hash the public key, and they encrypt their current location and a timestamp with the public key, and they send it to the server. And then the server stores a database that looks like this and maps hashes of public keys to lists of encrypted locations. And then when the owner of the device, who remember has the master beacon key and therefore can derive all of the subsequent timestamped public keys, when they query the database, they just hash the current public key that they're interested in, say for this day or the previous day or 7 days ago, and then the server will give them back all of the location reports. They'll expire eventually after around 10 days, but that's a parameter set by the server and not an inherent part of the protocol, and that's just how Apple does it right now. And so that's basically how the protocol works, and so it works pretty well. It's very accurate, and it's very effective for finding things. If you've ever used one of these, you know how close it gets to the devices that you've actually lost. However, there are some problems with this approach and with this technology. So malicious tracking is a real serious problem. And when I say malicious tracking, I mean using an AirTag-style device to track someone who either doesn't know they're being tracked or doesn't want to be tracked. And so malicious tracking was immediately seen to be a problem the moment these were released. We found a few mainstream news articles about malicious tracking being detected and noticed for a variety of sort of malicious use cases. People were stealing things with it. People were stalking each other with it. It was abused in sort of domestic abuse type situations. There's all sorts of awful things that people have done with these tags because they're so cheap, they're so easy. You can just buy one for $30 and drop it in someone's wallet or a purse or a car, and then all of a sudden you know where they are at all times. Right? So this is a little scary, to me at least. And so this is a serious problem, and our goal in this paper is to try to solve it and make it so that it isn't as bad anymore. Okay, so Apple also was worried about this problem when they developed the AirTags, and they have a solution called an item safety alert. And actually, there's a talk in this session that'll talk about them in more detail on how they work. But this is what one looks like. Okay, and so the idea behind the item safety alert is that since the beacons remain fixed over a day, you can listen for the beacons, and if you see the same beacon, if your smartphone sees the same beacon for a long period of time and over some distance, then it will alert you and say, hey, there's something tracking you, here's how you can find it, here's how you can disable it. So this is a good idea, I think, but unfortunately this approach is fundamentally flawed. And also, not just Apple implemented this, but there's an Android version of this software, and there's also an open source version of the software. They're all does the same thing. It looks for the beacons, tries to find ones that are the same, and flags them for you and says, hey, there's a beacon following you. But in previous work, we noted that this won't work. And the reason that it won't work is because Apple doesn't know the beacon keys. And so, therefore, we can use any valid public key, and anyone can generate a beacon however they want. I can generate a beacon from my computer right here, or you can program a small device to generate beacons if you want to, and they'll all be retrievable, and they all will work to do tracking. Okay, so if you want, you can program a custom device that rather than sending the same beacon, which is detectable, you send different beacons every minute, every second, every 30 seconds, whatever you want, and then none of the software that's deployed to detect tracking will flag them. It'll just look like you have too many AirTags near you, and you don't know what's going on. Maybe you're in the middle of a big city, who knows? So this is a problem, and this is the problem we're set out to solve in this paper. The first thing we did was we tried to formalize the security definitions for the properties that Apple's Find My network actually provides already. And so they tried to develop some privacy properties when they developed the protocol pretty clearly. And so the server isn't learning your location. The beacons and owners and tracking devices aren't linked with respect to the server, at least through the bytes that are sent in the messages, which is all privacy properties against a malicious server on behalf of the users. So we introduced a new definition, which is called beacon unforgeability, which says that for every time period, T for every day, and for every AirTag, there's only one valid beacon that can be retrieved. So that's the big goal that we wanted. So if you buy an AirTag, you get one beacon a day. If you want more beacons, you have to buy more AirTags. That's the property that we're interested in. And we achieved it with a new protocol. So the big idea here is the server can actually distribute a set of keys to each AirTag that are valid when the pairing occurs. But this will link the keys to the owners. And we also need to bind the keys to the timestamps. Because otherwise, you can get 300 keys and rotate them all very quickly. And so what we did was we deployed partial blind signatures, which is a cryptographic primitive that is a blind signature with a component that is not blind, and we put the timestamp there. So what happens during pairing is you get a year's worth of keys, each one for each day, and each key is only valid for the day that it's assigned to. And the idea behind the protocol is all you do is you get the signatures during pairing, the owner does, and then when the tracking device wants to broadcast a beacon, they broadcast a public key for which the owner has the signature. And then the reports are identical to the original protocol. And then finally, to retrieve them, you need to present your token. You need to present the signature of the key that you want to retrieve. So you can only retrieve keys for which you have a valid signature, and you only have one valid signature for every day, for every tag. So that's the basic idea behind the protocol. This makes minimal modifications to the original protocol and I think should be easy to update. It's basically a firmware update and then a change in pairing and a change in the report retrieval, which is mostly server-side. And we validated the issues that we thought might change. We built this custom AirTag stand-in. This is called a puck.js. It's about $30. It's about the same size as an AirTag. And we verified that it works on that, built an end-to-end implementation with an iOS app, a server application, and the puck program to send the beacons, and we made sure that it all works. The puck has enough storage, so an AirTag should as well, and it's fairly efficient. So pairing takes about 4 seconds for a year's worth of keys. So you do have to repair with this protocol once every year, and it takes about 4 seconds to complete. So we thought it was a reasonable solution to the problem, maybe not the only one, but a good one, just using a little bit of cryptography. So if anyone has any questions, I'm happy to answer them.
A reminder that if the audience has any questions, please feel free to post it on Zulip. Okay, we have our first question. Would you say your proposed solution need a similar update to be made for the Android/open source protocol?
So I'll try to answer. So that could either mean the Android open source protocol to detect malicious trackers or the Android protocol that's being deployed for their Android tracking network. For malicious tracker detection, this is going to make sure that the malicious tracker detection works, whether it's Apple, Android, open source, right? It's forcing the beacons to be the same throughout the day so that they can be detected by anyone. This protocol is proposed to replace Apple's crowdsourced location tracking service, so it doesn't have any bearing on the security of any other proposed location tracking service, like the Android one or the Samsung one, or sorry, the Google one or the Samsung one.
Okay, thank you. And we have a very practical question. Did you contact Apple to use your implementation?
We didn't contact them about the implementation. We did contact them about the vulnerability with the previous work, so they're aware of it. And we've had this published for a while, so hopefully they've seen it, or at least here, and could maybe think about deploying it.
I'll follow up with another question from my side. To what extent does the security definition and new protocol still allow malicious tracking?
So like I think I mentioned previously here, that all our definition does is it requires that for every time period, you only get to send one beacon per serial that you have, but a serial is sort of a stand-in. It's supposed to be stamped on the AirTag itself. So if you want to rotate keys more quickly, you can buy multiple AirTags, get multiple serials with this protocol, and then rotate them fast. But then the idea would be that if you have to buy, say, 200 AirTags or 100 AirTags, then the cost of it is approaching other tracking devices. Right? So it's eliminating its effectiveness as a cheap, simple, clean, easy tracking device. Now you have to buy 100 AirTags and then glue their key material together and write new software to figure out how to do it. It's much more complicated and approximates other tracking solutions in cost and time. So it's not a perfect solution.
Okay, if there are no further questions, thank you so much, Ellis.